Welcome back. So, as you can see by the title, we've gone back an episode. We've gone back to the numbered 8 episodes, back from 9. I'll tell you a little bit about why we're doing that. So, I was having a lot of problems getting the video to do what I wanted to do, and I decided to take a step back from it to think about the issues that I was having with the video. Namely, I was just starting to stray into the waters of getting the color burst signal working and figuring out the phases and the timing to make pixels actually come out in color. And I was running into issues where the color burst would not be on the correct phase. Basically, the microcontroller running the video there runs at about 28 megahertz, and the color burst is 3.5 megahertz. And if those two things start kind of out of phase out of each other, your colors can change because you're generating pixels at different parts of that 3.5 megahertz waveform, and that's an issue. So I have to think a way to try to sync up all those signals in order to generate that video, and I had to step back and think about how I wanted to do that. And one of the ways I found, to clear my head is to just stop where I am and go work on something else for a while until I come up with a better idea. I have 3 ways of thinking about how I'm going to correct that. I'm either going to use the microcontroller's built-in pulse width modulation generators to make the different clock frequencies I need for other things effectively, and then as long as I'm starting up those pulse width modulation clocks at the exact same time everything else on the microcontroller is starting, everything should always be in the same synchronization, so I shouldn't have to worry about timing issues. I could also pull all the clock generation into extra pins on the microcontroller, sit in a super tight loop, and read all those pins. And when all the clocks come in together at the right phase at the right time, then jump out of that spin loop and into the actual microprocessor operation. And hopefully that will keep things in phase. Maybe it will, maybe it won't, I don't know. Or I could bring all of the clocks in into probably like a 3-way exclusive or something like that. Bring a couple of the clocks in along with the reset pin to make sure that reset it comes low and then comes back high all at the same time when all 3 clocks are down at the same time and up at the same time, so everything lines up. I don't know. I have lots of different ways I can do that. I'm probably going to do the pulse width modulation thing because then everything is controlled by a single single crystal, and it's all internally timed and synchronized perfectly every single time on the microprocessor. But whatever. So let's go back to why I went backwards here. I decided to go back to the keyboard. I was sitting and I was thinking about the keyboard itself, and if we'll take a look down here, you can see that I've rearranged some stuff, and I used to have the keyboard set up with its own control chips and all that stuff over on a separate board, and I was thinking, the way I was talking to the keyboard, whether it was reading or writing or whatever, was through a ROM. And it's this big chip, and it's a big $2 chip, and it's relatively inexpensive, but it's this huge chip and is a big waste of board space and material and all of that stuff. And I originally thought about doing that because, okay, well, then I don't have to, wire up all this logic to do it. But then I thought, well, once I designed the keyboard, which this ROM was really good for figuring out the logic of what I need to do, because I can just write the ROM until it works the way I want it to work. Once the keyboard is designed and the interface is designed, I never have to change that again. This isn't a ROM that's, I'm not going to be fiddling with it a lot. So, I thought, well, what is the simplest way I can create keyboard select logic to do that? And I came up with a way of doing that. There's effectively, it's a combination of a 2 to 4 address selector and some diode logic to help select those lines, basically. So I was able to concatenate all of this into this stuff right here on the board. So let's take a look at all of this real quick. Effectively, these three chips here, the status serial register, the byte serial register, and the LS08 chip that helps us determine how we're latching our data in on the register clock. This didn't change. None of this has changed. But this right here has replaced that ROM chip. A single chip, some diodes, and some resistors replaced that ROM chip. And this, all told right here, is half as expensive, probably less than half as expensive as that ROM chip. So it's even simpler, less expensive implementation. So let's get into how I designed that implementation. I have some sheets of paper here with some drawings. So this, if we can see that, is it too exposed? That's a little better. So this is the basic design. I used a 74LS139 chip that can take two inputs, A and B, and give us four outputs. Basically, it takes a 2-bit value and gives us a 4 selection output. Because the only two lines I really need to select on are the first address line and whether we're reading or writing, that worked perfectly for the signals here that I had to send out. Now, there is a third signal, if we remember from the last time I went over this, is the keyboard select signal that I was using on the ROM to determine whether I was outputting these values or not. But I found, this effectively is just an enable signal. So what we do is we pull that into the chip enable for the LS139. So if KB cell is not selected, this is all just, all of these lines are unselected at all times, no matter what's on these two pins. So it basically does the same job. This one chip does the same job as that ROM. So, we kind of went from address decoding logic to a ROM back to address decoding logic, but in a roundabout way by doing that and using the ROM to help me figure out how the logic really worked, it helped me clean the logic up and make it even simpler. So what we have here, though, are the address decode lines going out to our selection lines. Pins 0 and 1 are commoned together effectively to bring the keyboard SR clear. What this means is the 0 address here references writing to one of the status registers, and 1 references writing to the other status register. And as we remember before, I don't care which register I write to. If I'm sending a write command anywhere into the keyboard memory space, it's clear the registers. That's basically all there is there. The 2 and 3 bit values 2 and 3 that come in on these help me determine whether I'm trying to read the keyboard byte value or the keyboard status value effectively. So when you combine those with that bit structure, as I have written out up here with our RW and A0 lines, RW0, if RW is 0, either one of those, meaning RW, when RW is low, that means a write is occurring. That means clear register. And then if RW is high, but then we're selecting either the status byte or the key byte based on the AO address, which is the low address of the beginning of the keyboard register area. So that's basically how I got that all set up. Now let's take a look at this part of the logic right here. This part effectively acts kind of like a ROM for us. It's a little bit of ROM encoder logic combined with this. So with the diode selected here on this part, it makes sense. That means if either, it kind of acts as an OR circuit. If either one of these two are selected, it will bring this line low. We have that pulled high by a 1K resistor at all times, just to ensure that this stays high no matter which one of those is high or low. It'll stay high until it's pulled low, then it stays low. I had the same logic here. We've got our pull-up resistors to ensure that these stay high at all times until these float those pins low, and then it drives it low. Basically, it pulls it to ground through the diode here. But because of the diode, if these are putting out a high voltage, it won't double the voltage up. Now, looking at this, I can probably make this even simpler. I probably only need my diode logic on these two, since we're combining those two. The diode logic probably is not literally required here, so on another run, another iteration, I'll bet you I can remove these diodes and these resistors, because these two lines, or these two wires, can drive these two select lines directly, and I shouldn't need this pull-up stuff. But this is what I came up with to try to emulate basically a ROM encoder effectively. I think this is overkill for that design, but I left it in because that's what I came up with, and it functioned. So that's just a note here that these diodes and resistors, at least on these two, probably are not required, because they're only driving a single line. Here it is going to be required because we have two outputs coming together, so that either one of these is going to select that SR clear. And again, this effectively acts like is it an OR or an AND? It acts as a logic circuit, so that if either one of these goes low, the whole thing will go low. The diodes help basically prevent backflow out of these when they're high out onto the circuit, and this is what's providing the high level instead of these two. Does that make sense? I'm going to go over that again because it barely makes sense to me. Basically, again, because these two are because either one of these could pull SR clear low, and we want either one of those to pull SR clear low, we tie both of these together with diodes with a pull-up resistor, so that the high value of this is making sure it's always being pulled by the 1K resistor, and that if either one of these goes low, the 1K resistor will flow through here to the whichever one of those values is low, and flow through the chip to ground. So the chip is bringing the ground through, if that makes sense. But because of the diode here, if this is trying to push any voltage back this direction, it hits the diode, and the voltage will not be supplied over this pin. So it allows either one of these, or both, they would never be both, but either one or both of these to go low, and allow this pin to actually go low by this one supplying the voltage instead of these pins supplying the voltage, if that makes sense. So that if this one's low and this one's high, this circuit will still go low because the voltage is coming from here, not from here, if that makes sense. And then on this side, it doesn't matter because we're not doing combination. These can just go away. I don't really need these diodes or resistors there, but they're in there now, and it functions, so I'm going to leave it as it is for now. I know that's kind of convoluted and a bit of a mess, but I am learning as I go. I'm learning my lower-level combinatorial logic using diodes, resistors, pull-ups, and pull-downs, so bear with me as I do that. So we'll bring JCM back in, JCM-1 back in here. Let's take a look now at the schematic of how this this looks. So before, the keyboard interface stuff was on the actual, keyboard schematic itself, but because it was on the keyboard board. But since then, I've pulled all of that logic into JCM-1 off of the keyboard, so it's on JCM-1's actual schematic now. So let's see if we can't get that in camera, in shot, and take a look-see. So we have a new keyboard connector, as I talked about last time. It's an 8-pin connector, so I have that represented now. Here's our 139. We have our KB cell as our select line for the entire chip, and we have our write coming out of our RW map chip, and our A0, so we can tell the combination of those two logics. And then those come out as our values of 0, 1, 2, or 3, which then again come out and are combined together with the pull-up resistor and the diodes to either make our SR clear signal for clear both status registers, our KB status output register, our KB status output enable register pin, so that if I'm reading the status, this will be active, and it'll activate that one, and this will put its data on the bus. And then the KB byte output enable. So if I'm reading the byte value, this will go low, select that, and it will put, the byte register will put its data onto the bus. This logic here is the same. This is the LS08. This is just our our logic circuit here, that our logic circuit that's this kind, because I don't remember what my logic circuits are, that combines these two signals so that when both of those signals are active, the keyboard is being clocked only at that same time, effectively. And of course, our 74HC595 register, our two registers for our key byte and our key status, again, those aren't any different. Those are the same as they were before. Since I did change, and I didn't show this on the last episode, since I did change the chip that's inside the keyboard, both for it to be less expensive and for the chip to be a lot smaller, I figured I should probably get that written up on the schematic, and I have done that. I show the new connector, and I show the new microcontroller. The pins on the microcontroller are effectively the same as they were before. However, they're arranged a little bit more logically. They make a little bit more sense. For example, these pins right in a row correspond directly across to the actual keyboard connector pins, so that makes sense to just run those lines straight over as a bus. Then all of our rows are in a line, and all of our columns are in one line to make the wiring a little bit simpler on the board there. Effectively, this code is identical to what it was in the other chip, as I already said. No real change there, just some small tweaks to tell it which pins to use, and a little bit of tweaks regarding the clock generation, because the chip uses slightly different. This chip uses slightly different terminology in the compiler for whatever reason. I couldn't compile it right. I had to tweak some registry settings. I don't know why. Or register settings. This is the updated schematic for the keyboard itself. Again, this is just a small version of that I showed, but I also wanted to show the updated switch matrix. Not hugely changed, it's mostly stuff on this side of the board and over here to show the extra row of keys that were added and some of the extra function keys we added. All of the keys on the new keyboard are completely decoded, so by reading either the byte or the status register, I can tell the status of every single one of the keys on this keyboard and take appropriate action. The last little thing I wanted to talk about on the keyboard was, on the last keyboard video, I had some problems putting some commands into JCM-1 from the keyboard itself, and I thought it was some software bugs with the way I was pulling in code from the keyboard. It's not actually a software bug. There is some sort of weird hardware bug with the status register and clearing it. When I clear the status register, there's some sort of value float going on. I don't know. That value float issue was on this, and it migrated over to here when I moved this circuit over directly. So I have a minor design problem somewhere in this part of the design. I don't know what it is. I don't have any floating inputs or outputs or anything. There's nothing wacky. But what happens effectively when I zero out the status register, it doesn't zero out immediately. It can take 10 to 20 clock cycles of the 6502 for it to finally float down to 0. However, the byte value will clear immediately. I don't know what's causing that. But basically, what was happening, if I would type a key on the keyboard, my code would fetch the byte from the byte value, put it in the accumulator, then clear the register to clear both of these simultaneously, which would result in the byte value becoming 0. But this would still have the status set to I have a key waiting. So what would happen is this guy would loop through several times as if you were smacking the key super fast. And it would read a whole bunch of zeros after reading the first character I actually typed, and it would stuff the buffer with a whole bunch of junk. And then when you would hit enter on the keyboard, the command interpreter, the monitor interpreter would go, see all these zeros, get confused, and say, well, you're trying to type an S command, but the command is invalidly formatted. Error, and it would throw an error on the screen. It wouldn't execute commands correctly. If I tried to list memory anywhere other than at the 0 location, it would try to list memory in 0 because it would effectively receive, it was as if you're typing L by itself. It wouldn't receive an address value and things like that. long story short, because of whatever this hardware glitch is, I don't know what it is. I will figure it out and solve it eventually. Because of that hardware glitch, I had to change JCM-1's keyboard read code just a little bit. Immediately after reading a key out of the keyboard, it will go into a tight loop checking the status register. It will zero it and check it and zero it and check it and keep doing that until it actually reads this as not having a key anymore. It only, like I said, it takes very few clock cycles of the CPU to do this, and the likelihood you're going to press another key in that time frame and actually like lose a key is effectively zero. And it gets rid of the glitch I was getting in actually typing in commands and things from the keyboard. But, you know, that's just a temporary software fix for a hardware problem. But I did want to mention that since, you know, we had that problem in the previous video. Well, that's really all there is on an update for JCM-1 for now. I just wanted to clean up that keyboard functionality and get it fully integrated into the board before I continued with video. Now, again, it also gave me a little bit of a kind of a respite from dealing with the video thing that was making my brain hurt. So what is coming up next? Well, I got to get back to the video. Keyboard is effectively done. We've got sound, we've got input-output on serial, we've got all of those bits and pieces, but that one last thing that's going to make this thing complete is getting that native video done. And I just got to get down to it and get it done. The problems with color video, I might step aside from color video for a little bit and just get the actual graphics working and not worry about the color generation. I'm not sure yet, but that's really the next step. Hopefully it'll stop making my brain hurt and I can get that done. So that's where we are. Well, that's all for today's episode. I hope you enjoyed it. Shout out to all my Patreons out there who help me out. You guys help me run the channel. I really do appreciate it. While you're here, hit like, subscribe, the bell, the thumbs up, and all of that YouTube-y stuff. It helps out the channel, helps out YouTube, help you guys find cool content to view. While you're here, watch some of my other videos, and remember, 8 bits are all you need.